We will often use Dirac notation in writing equations associated with angular momentum. We could write, for example, L squared operating on this ket here, and we've put in the indices for L and M inside the ket. We'll presume that we realize we're talking about spherical harmonics, and these then are the indexes or indices for the spherical harmonic. And similarly, we have it on the right-hand side as usual for our eigenequation. And we write that instead of writing everything out with the spherical harmonic function. There's no difference between these two equations, but this one gives us a shorthand form. And the LZ equation, we could similarly write LZ operating on this same ket here equal to MH bar on that ket, where this ket, we understand, is this spherical harmonic, instead of writing out the spherical harmonic here with its theta and phi in it. A common notation in atomic physics is the SPDF notation, and the spherical harmonics, of course, come up in the solution of the hydrogen atom problem, and different values of L were observed by spectroscopists in the 19th century to give rise to different sets of spectral lines from hydrogen. Now, at that time, they did not know that these were parameterized by this number L, but nonetheless, they could see these groups of spectral lines, and they called them the spectral set, the principal set, the diffuse set, and the fundamental set. Now, it turns out these terms here have essentially no meaning other than to give us these letters here. They don't have any physical meaning in and of themselves, but they do in fact correspond to the different values of L. So each of these is now identified, as I said, with specific values of L, and we can also alphabetically extend this series to higher L values. So we end up with the following notation, which is very common in talking about atoms. L equal to 0 is notated as S, L equals 1 is notated as P, L equals 2 corresponds to D, L equals 3 corresponds to F, and then from that point on we just go alphabetically. So L equals 4 would correspond to G, L equals 5 would correspond to H. It's rather convenient that the S wave functions are actually all spherically symmetric, but the S of the original notation had nothing to do with that.
Now then, we've understood the solutions of a somewhat abstract problem, the eigenfunctions of angular momentum operators in quantum mechanics. Of course, we've been doing this so that we can go on to solve one of the most important problems in quantum mechanics, the one that lies at the core of all of our basic understanding of chemical elements, the hydrogen atom. These spherical harmonic functions in particular turn out to give us all the angular properties of the atomic orbitals in the hydrogen atom. Looking at that whole hydrogen atom problem will be the subject of our next section.